This video is about the number e. This is an irrational number, sometimes called the banker's constant, and it's approximately 2.718281828, continuing on forever. So when we talk about the number e, we like to talk about how that number is defined. It's defined as the value of 1 plus 1 over n raised to the n as n gets larger and larger, grows without bound. So to show you what that looks like, we're going to make a table of values and just let our n values increase. So we're going to start with a couple of small values, and then we're going to start increasing that significantly. So we'll say 1,000, we'll say 100,000, and we'll say 1 million. Now we can put this in our calculator again as a y1, and then use our second function, calculate a value, and then just change the x value at the bottom of the screen to find these values. So that's what I have done. And my values, when I plug in 1, I get 2. When I plug in 2, I get 1 plus 1/2, so 1.5 squared, which is 2.25. When I plug in 10, I get 2.5937425. Plugging in 100, we get 2.7048138. And you can see the change here. That's about 0.25. We're growing from 0.25 to 0.59, so on. 1,000, we get 2.7169239. At 100,000, 2.7182682. And at 1,000,000, which is a huge jump in the x value or the n value, we get 2.7182805. So you can tell that as the numbers get larger and larger, that these values are not changing too much. And it turns out that this number will approach e, so if we make that get bigger and bigger and bigger, then this is going to approximate the number e, which is irrational, like pi, it goes on forever. And we have 2.718281828 repeating. I shouldn't say repeating, but continuing. Now, let's think about the graph of that. Well, we've been talking, if you've watched the other videos, about exponential graphs. And in this particular case, we have A being 1 and B being E. And since E is greater than 1, this graph should be increasing. So we know that exponential graphs have a horizontal asymptote at the x-axis. It goes through the point 0, 1 and 1e, which is approximately 2.718, so you can see that there, and the graph is in fact increasing. What we would like to be able to do with this number, for starters, is use our calculator to find the value and round it to 4 decimal places. And there are 2 ways that we can do that. So there are 2 places on your calculator where there's an e. The first one is if you use your second function, and then right above the division symbol is the letter E. So if you do second function division, it will come up with the letter E on your screen. That's good if we don't need to raise that E to any kind of a power. The second option is to use your second function, and then there is a key on the left-hand margin that says ln, and above that it will have e to the x. So when you do second function ln on your screen, it will come up as e and then a little flashing box that will allow you to plug that value in. So we can do these any way, either one of those two ways. You might want to pause your video and try those, and I will write down the values. So hopefully you got those values there. Remember, anything to the 0 power is 1, so that one should have been easy and no calculator required, but certainly you can use your calculator to do that. So now that we know what the graph of e to the x looks like, we can shift this graph around in the same way that we shifted other graphs. In this particular case, this first one, we have put a minus sign in front of the x, which means that that original graph is going to reflect on one of the axes, and because it's in front of the x, it's going to be on the y-axis. So just so we have a frame of reference, I am going to sketch just e to the x in yellow. So we know it'll go through 0, 1, and 1 e, so it'll look something like this. And we're going to reflect it on the y-axis, so the 0, 1 is not going to change, and this graph is going to be decreasing. So for this graph, the domain is all real numbers. The range is 0 to infinity. Oops, I should make this, this here should not be a bracket. It should be a parenthesis because we're never going to be 0. It's an asymptote. And our horizontal asymptote is the x-axis, which is y equals 0. So again, for this second example, let me sketch e to the x in yellow. And in this particular case, we are going to take the graph of e to the x and we're going to shift it left 3 units. So instead of 0, 1, it's going to be at negative 3, 1. This point here at 1e is now going to be at negative 2e, and we'll get a similar shape but just shifted to the left. The domain is still all real numbers. The range are the y values that we're going to have, so 0 to infinity. And our horizontal asymptote is again 0. For our last example, we've got quite a bit going on here. I'm going to rewrite this as minus e to the minus 0.5x plus 1. I do that because it kind of helps me see that this is up 1. Multiplying by a negative, not the x, but the function. This is going to be a reflection on the x-axis. This negative here is going to be a reflection on the y-axis. And since this value here is less than 1, this original one would be decreasing. So again, let me sketch the original e to the x. We know that that's going to be decreasing, so that might look more like this. And then we're going to reflect it on the x-axis and on the y-axis and shift it up 1. So shifting it up 1 is going to change my asymptote. And we're going to go through a couple of points here. It's going to look like this, because we've reflected it on the x-axis, then we reflected it on the y-axis. Well, reflection on the y-axis makes it go the red, and then on the x-axis makes it go below, and then we shifted it up 1. So for this example, our domain, again, is all real numbers. I can plug in anything I need to. My range, however, is going to be from negative infinity up to my horizontal asymptote here at 1. And that horizontal asymptote will be at y equals 1. So that's good practice. You can also do those in your calculator, but it's kind of a nice way to understand all of the graph shifting. So we like to be able to talk about our continuous growth or decay formula. So we've already taken a look at this. This looks slightly different because in this particular case we have an E here rather than we had just a B value. But when we're talking about continuous growth, that's going to use that E in our formula. So we have A of t equals AE to the RT. A, again, is going to be our initial value. R is going to be our continuous growth rate per unit of time. So that's, if we're working in business applications, we're talking about percentage of interest rate. And T is going to be our elapsed time. Now keep in mind, we don't just have applications in business, but we could be talking about population growth or bacteria growth. We could talk about depreciation of a vehicle, lots of different examples. So if R is greater than 0, then it's going to be continuous growth. And if R is less than 0, then it's going to be continuous decay. That would be something like that depreciation of a vehicle. For business applications, you may have seen this before. Rather than using A, we use P, meaning our principal, which again is our initial value that we're going to invest. And R is probably an interest rate per unit of time. And remember, this has to be as a decimal. So if it's 6%, we're going to use R equals 0.06. Okay, so let's take a look at an example. A person invests $5,000 at 12% interest rate per year, compounded continuously. So this is the word that tells us that this is going to have the form PE to the RT. In this particular case, our P, our initial investment, is $5,000. Our R is 12%, so 0.12. And this really is just a formula. We'll have 5,000 E to the 0.12 T. So this would be the exponential growth model. This is the model. And if we want to know the investment after 25 years, we would find A of 25. So in this case, 5,000 E to the 0.12 times 25. And your calculator will help you do that. In this case, we get 100,427.68. So we get $100,000, 427.68 cents. Keep in mind that this is the word that tells you what formula we're going to use. And I did notice that I have a little bit of a typo here. This should say what.